So welcome everyone to the December meeting of the Science and Engineering Council of Santa Barbara. I'm Mary Howe Grant, a past president of the organization. And first of all, I'd like to say thank you to our sponsors. You may see them on the screen: Community West Bank, Minot Enterprises, Bengal, and Toyon, all local companies. Membership renewals have now gone out, and I would ask you to please renew. Membership comes, as you know, it's $50 per annum for individuals, and it comes with free meeting attendance. And for those of you who are employed by a company, we'd like to encourage you to get your company to join as a corporate sponsor. Another way to get free meeting attendance, because if your company is a corporate sponsor, you do not have to pay to attend meetings. We'd also like you to think about becoming more involved. We're always looking for board members and people to work on committees. So let any of us who are board members know. And speaking of board members, here today are myself, obviously, Yvonne DeGraw, our program chair, Bob Lilly, Stephen Skopak, Joseph Stronks, and am I missing anyone else? If I am, please wave. Cheryl Ebner is the secretary of our organization. Okay. We also want to say thank you to those who donated to the SEC when registering for this event. And you should know that these donations basically help with our ongoing administrative costs, as well as help support our science fair awards. And if you would like to know more about the science fair, either go to our website or please ask. Okay. I would ask you, in addition, that in your year-end giving, you might consider the Science and Engineering Council's scholarship. We give scholarships through the Santa Barbara Scholarship Foundation. We've been fortunate to be able to give two small-ish awards that are STEM awards to students in Santa Barbara County. The donations to the Scholarship Foundation go directly to them. So please make certain that Science and Engineering Council is either in the memo of your check or it is clicked in the, I'm telling where this should go. So there's a line that says what particular scholarship one should want to support. And we would hope that you would support the Science and Engineering scholarships. Those are given out every May. And then finally, I'd like to introduce our program chair, Yvonne DeGraw, who will tell us about today's speaker and maybe even a couple more talks. Thank you.
Great. Thank you, Mary. Thanks. Hello, everyone, and welcome. Our next meeting will be on January 11th. I'm actually still in the process of confirming the speaker for that meeting. But we'll let you know about that by email. In upcoming months, we're planning interesting talks, including Professor Misha Shra from UCSB's Computer Science Department on artificial intelligence and its interaction with human behavior and perception at our April meeting, and Professor Ben Halpern from UCSB's Bren School on the environmental footprint of food production at our May meeting. As always, feel free to contact me about particular topics or speakers you'd like to suggest. If you're interested in our past meetings, we have a YouTube channel with recorded meetings from the past year or so. Subtitles are provided during today's talk if you enable live transcript in your Zoom window, and you can type questions into the Zoom chat during the talk or ask them after the talk. Today, we're happy to have Dr. Michael Baylor speaking to us. He's an assistant professor in both UCSB's departments of computer science and psychological and brain sciences, and is the director of UCSB's Bionic Vision Lab. He received his PhD in computer science from UC Irvine, as well as a bachelor's in electrical engineering and a master's in biomedical engineering from ETH Zurich. Prior to joining UCSB, he completed a postdoc at the University of Washington, where he started working on computational models of bionic vision. Dr. Baylor is the Associate Director of the UCSB Center for Virtual Environments and Behavior and a recipient of the National Institutes of Health Pathway to Independence Award, as well as the prestigious NIH Director's New Innovator Award. So we're happy to have you here. Welcome, Dr. Baylor.
Thank you very much for this nice introduction. And thank you all for having me. I'm really excited to tell you about my research today. As you could have guessed from the bio, I grew up in Switzerland and only came to the US maybe 10 years ago for my PhD, and started now on the tenure track almost 3 years ago, actually 2 months before COVID hit, which I wouldn't recommend. So we had kind of a rocky start, but now we're up and running, and I lead the Bionic Vision Lab, where I bring together students from computer science as well as neuroscience and psychology to study the science that underlies neuro implants, such as a visual prosthesis. And that's what I want to talk to you about today. Before I get started, I should mention, feel free to ask questions, either by raising your hand, speaking up, or posting in the chat. I'll try to keep an eye on the chat as we go along. Yeah, so especially if you have a clarification question, feel free. All right. Most of you are probably aware that blindness affects millions of people worldwide, and there are many causes that can lead to all sorts of degrees of blindness. In the developed world, the two most common causes are called retinitis pigmentosa and macular degeneration. Both of these are hereditary and lead to a progressive loss of vision. In the case of RP on the left, kind of leads to tunnel vision as you first lose your vision in the periphery and that moves inwards. And in macular degeneration works the other way around, where you lose vision in the fovea first. And so, although there is no cure for these diseases, researchers have been trying to come up with a way to treat them. I wanted to highlight some possible avenues here. One approach is gene therapy, because the faulty genes in the retina are a cause of these diseases. The idea is that maybe you could inject a functioning gene into the eye, and that might be able to slow disease progression or even revert it. Another approach is to use optogenetics, which allows you to make neurons that have never responded to light now sensitive to natural light or laser stimulation. And so if you had a clever projection mechanism, you could turn on neurons in the eye, which would then activate other neurons and communicate to the brain that there was a visual input. And third is the idea of an electronic prosthesis, basically a microelectrode array that can be implanted directly in the eye or the brain of the patient. And it uses electrical current to stimulate the surviving neurons. And again, if you do this in a clever way, you may be able to fool the brain into thinking that it saw something, because these neurons are usually involved in encoding visual information. And so this is the focus of today. It sounds a bit like science fiction, but there are actual companies out there and research groups that have been developing such devices for 50 or even 70 years. So there are two companies listed here who have commercialized devices. Unfortunately, both discontinued thanks to COVID and other reasons. But there are more devices in clinical trial right now. Some of which are developed on the West Coast. Actually, Stanford has a device in collaboration with Pixie Vision in France. But there are multiple devices all over the world that are either in clinical trials or in development. And so as of 3 years ago, I'm happy to put UCSB on the map as well as a research institution that focus on the basic research aspect of things. Now, as you browse through the list of these names, you may see that most of them look like biomedical startup companies, and that is true. There's only a small number of universities that are involved in basic research. And what kind of makes us unique is that we don't focus on one specific technology. We actually work with many different institutions to research sort of the underlying neuroscience and computer science that will make such devices possible. Just to give you an idea of what some of the state-of-the-art devices look like, this is the one I've already mentioned out of Stanford. It's called the Prima device. And what you see here is an array of photovoltaic cells. So every cell here is basically a little solar cell that can respond to incoming light and stimulate the neurons that surround it. This one is implanted directly in the eye, in the subretinal space. And here's another example that's in development out of Switzerland, which is an epiretinal device. It kind of looks like a contact lens. So every small little pixel here is an electrode that could be placed in the retina. And then there's an ever-growing list of cortical implants. I'm highlighting two different technologies here. One, the Orion implant out of Sylmar, California. It used to be developed by a company called Second Sight and recently changed its name. They develop a surface electrode array. So this goes here on, you have to open up the skull and place it on top of the cortex. And so these are large surface electrodes array that try to stimulate all the neurons that surround it, as opposed to down here, a microelectrode array, where you have much smaller and finer electrodes that you can place more closely to the neurons. What all of these technologies have in common is listed here. So you start with the brain of a patient, and you need to provide some way of getting visual input into the brain. So there's usually some sort of external camera or a projector that sends a signal to some vision processing units, which you want to be mobile. This may process the incoming image, video, frame by frame, and maybe also optimize the stimuli that will be sent to the device that is implanted, as I said, either directly in the eye or the brain here. And then this microelectrode array usually stimulates the surviving neurons with electrical current. If you do this in a smart way, you may elicit neural activity, or ideally a visual percept, right? Because typically neurons communicate with electrical signals. If we artificially produce these signals, the brain may not be able to differentiate what is artificial and what is natural. And ideally, this would result in visual perception. So applied stimulus leads to some predicted response. Maybe the most famous implant before the Neuralink presentation was Argus 2, which was developed by Second Sight, as I mentioned, out of the West Coast. And this device had an external pair of glasses and a 6x10 electrode array implanted directly in the retina. This is shown down here. We could see the electrode array sitting on top of the ganglion cells in the eye. And as I already alluded to, the electrodes here are arranged in a grid, 6x10, relatively large electrodes. And so the assumption that has dominated the field for a long time is that you can think of this as a pixel grid, basically. And if you stimulate neurons spatially, then that should translate into a form percept. And so a lot of my research focuses on showing the limits of this or highlighting challenges with this approach. Of course, there are many open challenges that come with brain technology. Surgical, for example, you have to find a way to place the electrode array safely and securely so that they won't cause damage. You have to be able to fabricate ever smaller electrodes, again with safe biocompatible materials, make sure your packaging of the electronics is watertight, and so on and so forth. There's problems in electrical engineering. For example, you have to deliver currents to the electrode that are charge balanced. So typically this would be square wave pulses designed such that the net current over time is zero. So you don't leave any lasting charge in the tissue. And you have to be able to wirelessly deliver power and data to the implant. But in my opinion, there's another giant problem here, which is the neuroscience, the problem of translating electrostimulation into a code that the brain can understand. And because these technologies are targeted for people who have lost their vision, the implant has to communicate with a brain that has been blind for many years, potentially, and maybe has undergone plasticity and other changes that make it different from the brain of a sighted person. And so this really challenges our understanding of the neural code of vision, right? How does perception come about? How can we go from activity in populations of neurons to the impression that we see something? And so, as I mentioned, the basic assumption here is relatively simple, which is that there's a linear transform from stimulation to percept. For example, if you had an input image on your camera, and this is what you want to produce in the mind of the patient, the assumption is that stimulating a grid of positions on the retina leads to the percept of a grid of luminous dots, right? So-called phosphenes. If you build an array that only has 10 by 10 electrodes, then the image you may produce might look something like this, not very fulfilling yet. But if you just have many, many more electrodes, right? At some point, you should be able to create useful vision. Unfortunately, we know that this is not the case, at least not for the current technologies, because this so-called scoreboard model fails to predict real data. We know this because we have worked with real patients and we asked them to draw what they see when we stimulate their device. So typically you would stimulate just one electrode and you would ask them to outline the shape of the elicited phosphene on a touch screen. So here's a patient drawing of such a phosphene. You turn on just one electrode and yes, they are blind, but they still know kind of what shape they're tracing on the touch screen. And so this shape here looked nothing like a pixel, more like an arc, right? So maybe that's a fluke. Let's try again. Same arc, again and again and again. And of course, this is just one electrode in one subject, but as we repeated this across patients and across days, bless you, we found a variety of shapes that were elicited. So I'm going to show you a couple here. This is a particular subject's implant. We're going to stimulate this electrode called D3, and they draw on the screen. And the different colors here are the shapes from different trials. So the first thing we could do is we could align all these shapes by the center of mass and average. So we know on average, if you turn on electrode D3, you will produce a vertical streak. If you repeat this for all the other electrodes, for this subject, we found all possible streaks, basically. So seemingly random orientation, but across trial, it was highly reproducible, right? Because every streak here is averaged across 5 trials. So even though going from one electrode to another, you get a vastly different orientation, the orientation was always the same across trials. And even worse, different patients see these phosphenes very differently. So subject 3 had exclusively streaks. Subject 2 had some blobs or wedges that you may call a pixel, if you like, but there's still some streaky things here, or triangles and all sorts of geometric shapes that make it hard to that are hard to explain with the scoreboard model. So to understand what the cause of these distortions is, I have to give you a quick neuroscience crash course. We can start with the retina, the retinal physiology. I'm sure you're all aware how light enters the eye. It gets projected onto the back of the eye, which is where the retina is located. And the retina itself has a neural network organized into different layers. So you have your photoreceptors up here, the rods and the cones, which react to the incoming light and transduce that signal into an electrical one that is sent to the bipolar cells. There's some more processing happening here. And eventually the signal reaches the ganglion cells, which are the output layer of the retina. The ganglion cells then send their fibers through the optic nerve to the brain. And so what happens in diseases like RP or AMD is that you lose your photoreceptors, among many other changes that I'm not showing here. Thus, the idea of having an implant replace the lost functionality. There are different implant locations, some shown here. So the Prima device was a subretinal implant that goes directly here and interfaces with the bipolar cells. Whereas the Argus 2 that I just showed you, the 6x10 electrode array, that one is an epiretinal device. So as you can see, this sits directly on top of the ganglion cells. But not just the ganglion cell bodies, also the ganglion cell axons. And that turned out to be crucial. Is here, we're looking now at the back of the eye, a top-down view, basically. And all these fibers here are real axons of trajectories extracted from 55 different cadaver human eyes, aligned by the fovea, the center of vision, and the optic disc. And so the take-home message here is that this pattern of axons is highly stereotyped across people. Meaning if you are a ganglion cell that lives up here, I assume you can see my cursor, my mouse. If you are a ganglion cell up here, your axons, I guess I could draw, would follow this trajectory to the optic disc and then to the brain. Whereas if you're down here, you follow a different trajectory. But the layout, right, the spatial map is highly preserved across individuals. Meaning we can model this. You can ignore the math, but believe me that there's only a small number of parameters needed to build a patient-specific axon map. And so now we can start asking what would happen if you had an electrode right there and you stimulated the neurons beneath it. What would happen is you wouldn't just hit the ganglion cell bodies that are right below the electrode. You would also hit all of the axons that go through this point in space to the optic disc. And these axons might belong to different neurons that live maybe far away from the electrode, right? But as shown here, if you're the first neuron there, your trajectory looks like this. The other ones also looks like that, and so on and so forth. And you're turning all of these neurons on at the same time. Typically, when a ganglion cell is active, it encodes or it tells the brain that it saw something in a particular point in space. And now we're turning on this electrode here saying there is maybe a blob up there, but it was also right next to it and right next to it and right next to it. And so essentially what we're producing is a streak, an arc with just one electrode. So if this were true, we should be able to predict the orientation of the phosphine that patients saw, right? Just from the location of the electrode. And so that's what we tried first. The only problem is we need to build an axon map that is specific to a particular patient. We have to do that in vivo. We can't just extract or wait for the cadaver human eye, right? We have to do this in vivo to figure out where this particular implant is located. The data we have available looks like this. These are fundus images taken by an optometrist before and after the surgery. So before the surgery, this is a healthy eye. It's very easy to extract the location of the optic disc and the fovea. But after surgery, of course, the implant is on top of this. So how can you tell where the fovea is underneath the array? And so we had to be a little more clever and use computer vision, specifically image registration. So one way to do this is we could identify landmarks in both images. and then find the coordinate transform that tells us how do you go from the first image to the second one. You find the correspondence between points across images, and that allows you to put the two coordinate systems on top of each other. So now you have one image where from the first image, you know where the fovea is, and you can find the location on the fovea on the second image. There's some other tricks that we have to apply here that I will skip over, but basically you have to figure out where is the fovea in relation to the optic disc and how is your eye rotated. And you have to convert pixels to microns, which we can do because we know the electrode spacing. So there's a couple tricks we can combine. And what we arrive at is now a patient-specific simulated axon map. So we can place a simulated array on top of a simulated axon map exactly as it is in the actual eye. So far, so good? Okay, so then let's go back to the question about phosphene orientation, right? So if our theory were true, we should be able to tell the orientation, predict the orientation of a percept from the location of the electrode. We looked at that, we turned on single electrodes, we had them draw again. So even though this one here is fairly blobby, you could see that it is a little elongated along this axis here. So this is the axis we extracted and we plotted here on the left. We do this for all possible electrodes. Here it's easy to extract the axis, the orientation, and so on and so forth. Repeat that for all the electrodes we have, and we find that it matches pretty good. It lines up pretty good, right? But it's not perfect. Of course, these are drawings by blind people, so there might be some error just in terms of their drawing ability or some variation across trials. So if we compare the orientation of the drawing to the orientation of the axon that is right below it, we will get a distribution of errors, right, across all the drawings. And so the question is this distribution of errors good enough? How would it compare to a random placement of the implant, for example? You could do a bootstrap, right? If it is really the axon map that causes the orientation of the phosphene, then any deviation from the true location should give you larger errors. So you could do a bootstrapping where you place the array randomly 1,000, 10,000 times on the retina. You extract the distribution of errors, and then you compare that to the one you found behaviorally and make a statement that the distribution here is significantly smaller than the one you would expect from a random placement. Long story short, this was the case for this patient and also for the other three that we had available. Here in panel A, there you can notice this is a different implant. This is Argus 1, the prototype. It had a 4x4 electrode grid, and then the other three are Argus 2 implants. And for all of them, we find that this axon map predicts the orientation of the phosphene fairly accurately. Of course, we want to go one step further, and we don't just want to predict the orientation, we want to predict the whole shape, right? The baseline model we have available is the scoreboard model that says everything's a blob. So what we could do is we could use the simulated location of the electrode. We could calculate the electric field basically, or it's kind of a tissue activation map that should drop off radially. And we threshold that to get a simulated image. So this is what a patient should draw if they had a scoreboard model in their eye. And we can compare this to a real patient drawing, right? And then figure out the errors. Alternatively, we can use the axon map to predict shape. And so the only thing we're changing here, we're now assuming that the current spreads with different decay rates along different directions. So there's one lambda that says how far does current spread along the axon. And there's rho that says how far does it spread perpendicular to the axon. And what you want to do is find a set of rho and lambda for every subject. We can do this by minimizing the error between the predicted image and the real image. And skipping over all the methods, here are the results. If we go back to the subject drawings and the scoreboard model, of course, here everything is predicted to be a blob. That's not interesting. But now if you add the axon map model, so you just give it one more parameter and allow it to be longer along the axon versus not, you can see that this model can produce a whole range of shapes that differ depending on the location of the electrode. And this worked well for subject 1 with the Argus 1 prototype, and it also worked well for the other subjects. So again, even though here some of them are streaky and others are more blobby, the model is able to capture this across subjects, even if you have a subject that sees exclusively streaks and others that have sort of a mix of wedges and triangles and lines. So that was the first big step. So now we have a very simple model that just knows a little bit about the neurophysiology, and it is able to predict the shape of these phosphines across different patients. This allows us now to study systematically how the vision would change as a function of these parameters. Here's an example. So what happens if you start increasing lambda, which is the current spread along the axon, right? If your lambda is small, then your electrode grid would basically produce a downsampled, blurry version of what you're trying to show. Here, the example of a Snellen map, right? A Snellen chart. But as you increase lambda, you increase the streakiness, and that can really smear out your shapes that you're trying to produce. And if lambda is really large, you might produce an image that looks nothing like you intended. There's another prediction we can make, which is what happens if you stimulate 2 electrodes, but they just happen to fall on the same axon bundle, axon trajectory. If you do that, the first electrode here should already activate all the neurons that send their axons through this point in space, right? So both of these electrodes should activate the same axons, thus leading to only one phosphine, which is exactly what patients are drawing in this case. But you could choose 2 different electrodes. They're the same distance on the retina. They just happen to fall now on 2 different axon bundles. And then you would predict that the patient is drawing 2 shapes, which is exactly, again, what they are drawing. And so this is a really interesting model to help us predict now what a patient would see when you turn on many electrodes at the same time and you want to produce different artificial shapes. Long story short, this is a function of where the electrode is placed on the retina. And rho and lambda are also patient specific, just because some draw it more streaky than others. And the shape also changes as a function of your stimulus, which makes the thing even more complicated. Now, as you increase the amplitude, you get more and more current spread, right? So naturally, the shape should get larger, blobbier. But as you increase the frequency, you produce more spikes, more action potentials in the neurons. And that is usually a signal to the brain that something is brighter. So then you don't change the shape much, but the brightness of the phosphine. And then the last thing you could change is the pulse duration. I should have had a little drawing here. So we're talking about these biphasic pulses, right? And we could change the amplitude, or we could change the pulse duration, or we could change the number of pulses, the frequency. And so all of these have a different effect on the perceived phosphines, on the vision created by the device. To make things worse, there's also distortions in time, not just space. So as you turn on an electrode, the phosphine typically come on. It's described as a flash of light. And if you turn on many, it's like watching a firework at night. And these phosphines, they don't stay on. Often they fade rather quickly over time. And so people have looked at how quickly these stimuli fade. The x-axis here is time in seconds. And what people had to do is with a joystick, they had to indicate the brightness of the phosphine. So you turn on the stimulus, that's the dotted line here, and patients say, okay, it's very bright. It stays bright until the stimulus goes away. and then it drops back to 0. That's a well-behaved example. You can see how that will work. But unfortunately, some patients don't see it like that, especially if you increase the frequency. Now the phosphene starts to fade, even though the dotted line, the stimulus is still on. And then for some, the perceived brightness even gets into the negative. So even darker than black, which is really odd perception. But has been reproduced over many trials. And then when you remove the stimulus, you get a little bit of a flash, a quick flash here before it goes back to 0. So this probably has all to do with how ganglion cells integrate signals in time. And again, we could build a model using 5 to 10 years of data. So I'll skip over that, but give you the long story short, which is we have developed models in space and in time that work for all the implants that we have available. And we've made a Python package. So you could all try it out if you like. The package is called Pulse to Percept. And you could choose an implant and choose a stimulus. And then the simulation will tell you what that should look like for a patient. And we hope that this will be very helpful for many people, right? For the families of patients who are trying to figure out, is it worth the surgery and the cost to get this new implant? It could help engineers who are trying to build new devices and want to know, how many electrodes do I need? How far away on the retina should I place them? And so on and so forth. And we also hope, we can talk about this later. There's the risk of overhyping a technology like this. And we hope that simulations like this can give us realistic predictions and inform the public of what a technology can and cannot do. All right, so I wanted to show you some examples, because now we have distortions in space and in time, which means we can start to predict movies. What would happen if you were in a busy subway scene and you're trying to find your way or catch your train? If we're assuming we have an Argus 2 in our eye, so 6 by 10 electrodes, relatively large, no axon stimulation yet, then what you would expect to see is this sort of blurry, downscaled version of the video. But now when we add axonal stimulation, you get these streaks. And so the percept starts to change. You can see it here in a severe example where everything kind of starts to bend. And it becomes really hard to figure out what's going on around you. That was only space. So if you also add time, again, this was the original example. This is just no fading, blurry downscale version. If you now add some of these temporal distortions, some people report flicker, then now you're looking at something like this. This looks like a very old movie, huh? And then things might desensitize over time. So meaning that over time, you would need more and more stimulation to keep the cells active. If you don't do that, then your flickering stimulus will just kind of fade out. And unfortunately, that's also what real patients report. They're instructed to look into a dark corner, for example, to let their eyes kind of recharge. And then you go back to your task. So both of these have been reported behaviorally, and now we might finally have a principled way of studying why that is and what impact that might have on their vision. The first thing you might ask is, well, 6 by 10 is not a lot, right? So can we just have more electrodes? How will that help? So again, for reference, this is the 6 by 10 with the axonal distortions. So now let's up the numbers. And now suddenly, slowly, we're able to make out some of the details, but also the distortions are really evident, right? It kind of looks like a fisheye lens of sorts. And there's no chance of reading a sign, for example, like up there. It does allow us to tell us when objects or people move by quickly or close to us. So it could be good enough for something like obstacle avoidance, just wayfinding. But probably, not for reading signs or object recognition in general. I mean, we still seem to be far off from that. Okay, I haven't received any questions, so I'll just forge ahead. This is where we believe the field is at, where current implants are at. Not, of course, where we ideally want to be. So a big part of my research is also to find ways to improve upon current technology. And I've shown you this slide earlier with the common components of an implant. What we have seen now is basically what we call a forward model. It's this mathematical description, right, of how you go from a stimulus to a predicted response. But really what you want is the inverse of that, right? I don't want to know if I apply the stimulus, how distorted does it look? I want to know how do I produce the letter A in the mind of the patient, right? For a desired response, what is the required stimulus? That's what I want to know. And so more recently, we've been thinking about this as sort of an encoding versus decoding problem. This forward model, you can think of it as a stimulus decoder, right? Because it tells you for a given stimulus, what is the response? And we can mess with the stimulus. We can use different amplitudes, pulse durations, frequencies, and so on. And we could use basic neuroscience data to help build this forward model, as I've just shown you. Here's some examples of axonal stimulation in the retina. And then we can compare our predictions to real behavioral data, as I've shown you with the shapes. There's also a lot of data about the perceived brightness of things over time or as a function of the applied current and so on and so forth. So we're very good at building this forward model, this decoder. But what is missing is the encoder, which is the thing I mentioned. What is the required stimulus to produce a desired percept? And so one approach to do this is to train the whole thing end to end. If you think about there is a forward model in the loop that goes from stimulus to response, you could learn a model that undoes F, so the inverse of F. You could put that in the loop, and you basically have an auto-encoded structure where this model here is trying to undo all the distortions encountered in model F. And then you would train this encoder in the loop by minimizing some reconstruction error. So you have the target response, the image you want to produce, and then the predicted response. You can derive an error from that and find the inverse model that gives you the smallest error. Just a question. Can the patient get an upgrade once the implant is in place? In other words, can the implant be removed and replaced? Theoretically, yes. Practically, it's going to be expensive. There's only one patient in the world who has 2 implants, one in each eye, and they're not allowed to use them at the same time. That's an interesting example. So far, it's been an issue as people participate in a clinical trial, for example, and the trial ends. Sometimes they have to explant the device again. And so that could be very traumatic for patients because they go from being blind to seeing something to being blind again. So yes, ideally you could upgrade, but it hasn't happened yet, or I'm not aware of any examples. Okay, back to the encoder. So what we want is to learn an inverse model that undoes all the distortions to minimize an error. So essentially what I'm saying, this is a regression problem. We're trying to minimize the error between a target output and a predicted output. Example, if we want to produce the shape of E in the mind of the patient, typically what is done, we call this the naive approach, is to imprint the shape of E on the retina, as shown here on the left. And we can use our model to tell you that won't look anything like an E. Right, because you have all these distortions from the axons. So it comes out that the other end does not resemble E. But that's exactly what you want. You don't want the left to look like E, you want the right to look like E. So if we do the inverse, and we try to find the stimulus now that gives you this predicted percept, it looks much more like an E. Here on the left, the size of the disc is proportional to the current you need to apply. So this is saying, you really need to activate only these 2 electrodes down here because we already know it's going to smear out to the left. So it's going to help us create the shape, these large streaks up here and down there. And so then you just need a little more stuff in the middle here, and boom, you have an E. You might say, of course, this is a kind of a simple example, right? Because the shape of E is already aligned with the bundles, with the axons. So let's look at another one. Would anyone like to guess what letter this is? Maybe, it's in fact an N. You can maybe guess it if you stared at these for years, like I did. But here's the better example. So if you optimize the stimulus, you get something that looks more like an N, but it's not without issues, right? You can see here, it's very challenging to produce streaks opposite, edges opposite to the bundles, right? Because as soon as you stimulate here, it's going to smear out to the left. So it's really hard to place a vertical line right here just because it's orthogonal to the axon bundles. Okay, one more example. What letter is this?
G?
G? Not
G?
bad. C? G? Z. Yes, and so again, here's the optimized example, and again, it's not without issues. Another thing, or I only briefly mentioned that changing the amplitude changes the shape, the size of things. So it makes things brighter just a little bit, but it also makes it larger. So that means you have to be very careful in choosing which electrodes to stimulate and which amplitude to use. And so that's why most recently we built the most comprehensive model we could to predict shape as a function of not just amplitude, but also frequency and pulse duration, all these other manipulations. And we studied it more systematically on a larger corpus of digits here. MNIST is the famous data set. And so this approach is called the HNA, hybrid neural autoencoder. And we compared it to the naive approach at the bottom. I guess we can ignore the surrogates. That's just another model that we use to compare against. And so if our rho and lambda, the distortion parameters, if they are small, then the optimization doesn't buy you much, right? It will look much like the naive encoding. But as soon as you increase the streak length, now lambda is really large, you can see that the naive and these other models, they do really poorly. And so this is really where you need the HNA optimizer, because it can still find the combination of amplitude, frequency, and pulse duration that produces the desired shape. Excuse me. Yes, and this is also apparent as you increase rho, which is just the blobbiness of things. In the naive, this quickly just turns into some bright blob without distinguishable shape. Whereas in the optimized approach, you can still see the digit. And yes, this is especially bad if you have both large and streaky phosphines. This is where the optimizer really shines. And so our hope is to, to test this with real patients, of course, because we do have the power now to fit the model to an individual. And so our next step is to test this, if we can compare to the naive approach, if people are actually able to do better at object recognition, or maybe simpler grading orientation tasks, things like that. But I think we can go further than that, because one thing I haven't told you about is that these implants, they really only cover a very small portion of your visual field. Maybe 10 by 20 degrees or so for Argus. And so that's like watching TV from across the room. And you're oblivious to what goes on in the periphery. And that means you need special bodily techniques to use this new artificial vision. What you need to do is you need to use your head to steer the camera on your head to the right direction. And you get only piece by piece of the visual scene. On top of that, what you get are these phosphenes, these fireworks, flashes of lights, right? That require you to use associative learning and deductive reasoning to figure out what's going on. For example, you already know you're standing outside in the park, and maybe first you get this percept of a vertical phosphene, very bright, and then you move your head up a little bit and you get this flickering star field. And that would allow you to deduce, oh, maybe I'm looking at a tree, where you first look at the trunk and then the leaves. So it's very different from natural vision. And any claims made that it is similar are dubious at best from what we know so far. In addition, visual outcomes are typically measured on behavioral tasks. So people jump from single electrode activation all the way to door finding or character recognition. And these are the tasks we have available to know whether the implant works. But it's really hard to simulate, of course. But virtual environments actually offer a nice way to solve many of these difficulties. If you think about how this task would be done by a patient, you have your implant in the eye, you stimulate the electrodes, and then you instruct the patient to walk to find the door in the room, for example. We could do all these steps in the virtual environment. Because we have the simulated model, we can fit this to the individual patient. We know how the implant is stimulated. We can simulate that as well. And we can have him walk around in the virtual environment modeled after the real task, and then compare the performance of these, what we call virtual patients, which are sighted individuals using the simulated vision. And we can compare their performance to real bionic eye patients. Yeah, so these are the virtual patients, sighted participants wearing a VR headset with the simulation that includes these biologically realistic models of the retina, and they can be fitted to an individual so that we can evaluate behavioral performance in maybe even dangerous tasks, right? So now use your implant to walk across the street or through a busy subway scene. We can simulate that in VR and train them in VR as well before they go out and have to do it in the real world. And so we did that, and I think I'll have much time to go into it, but I can show you some examples. So we re-implemented a hallway navigation task from the literature where they start down here, they have to walk to the other end of the hallway while avoiding obstacles. People that could randomly pop up in one of 6 locations, or actually 3 of 6 locations, 1 at each distance. We did this safely in the virtual environment, just a large room with, these are ropes to help guide them. This is what you would see in virtual reality. And then from there, we extracted edges of the hallway and the doors and the people, and fed that through our simulation. And so what it looks like is something like this. You can see the real view at the bottom, and then these streaks are these phosphenes that people see as they walk down the hallway. And yeah, it looks nothing like the real thing, right? And somehow you have to make sense of all these flashes to do the task. Now, this example has a very large row, right? Very blurry percepts. And now everything kind of smears together. Whereas this example had the streaky version of it. And so this also predicts that depending on the rho and lambda of a particular patient, they should perform differently, right? In these tasks. Yes, so these phosphene distortions may impede performance, right? And this is important to know because we have to provide realistic predictions of prosthetic performance, right? If we just assume the scoreboard model, then our predictions will be way off with respect to the real implants. And once we have everything in VR, we can again start thinking about how to improve performance, because now we can have them do real world tasks. So nothing stops us from using a better stimulus encoding, right? Or even use some computer vision. So for example, with a limited number of electrodes, maybe it's more important to just highlight the important stuff in the scene, right? You don't care so much about things that are far away or things that are not relevant for you right now, because we could use object segmentation to find the big obstacles in the room or the close by stuff and highlight only that. Or we, I guess I already kind of said it, we could highlight only nearby things. So we don't care so much what the identity is of the object or obstacle. We just want to know what is in our surroundings, in our immediate surroundings, and ignore all the stuff that is far away. Or we could find the outlines of the room to give people a sense of orientation, where they are with respect to the room they're in. Or we could use, this is called visual question answering. There's some neat neural networks. You can ask them a question and the network will respond visually. Like, for example, here, how many giraffes are drinking water? And the network would draw bounding boxes around the giraffes, but only the ones by the water hole, right? Not the one that is far away. You could imagine a thing where you ask, hey, bionic eye, where did I put my keys? And the bionic eye would parse all the objects nearby and then highlight only the keys for you. And of course, yeah, some edges to tell you where you are in the room. So yeah, there's a lot of fun use cases you can think of once this technology is able to operate in unstructured environments, right? And you have to do it in real time, all embedded. But this could potentially lead to what I like to call a smart bionic eye, one that combines artificial intelligence, computer vision, to provide visual augmentations to help you with real world tasks. So kind of moving away from the claim of restoring natural vision and just accepting that this artificial vision is different, but nonetheless useful, right? Because at the end of the day, what matters is that people can safely navigate or find their way around their daily lives. So that could just not just be a navigation mode, which highlights here sidewalk, roads, and obstacles. There could be a conversation mode. So now, often blind people have trouble identifying when someone is speaking to them directly or when someone leaves or enters the room. It often happens that, you know, you're still talking and the person has left the room and you're just silly sitting there talking to yourself. So it's really embarrassing. And there's a desire to better understand where people are around you and maybe who is speaking or who is even facing you versus not. And so this is a completely different a use case, right, that the bionic eye would be useful for. And we can think of many more, like, yeah, the misplaced keys, or what existing visual aids already do, like reading text and telling you not visually, but with audio, what you're looking at right now. So combining all of this into a smart bionic eye is I think, where the appeal lies. And we could use our simulations, our virtual reality prototype, to drive the development, right? So first, we could test these different ideas in VR, and then the ones that work, we could put in the effort and time and money to test it on real patients. And that's sort of where my lab is headed, combining all these insights from neuroscience and the algorithms from computer science, and build something useful, right, that can make a difference in real world tasks in an iterative design process, where you bring in end users and you work with them to design for them. Design with them rather than for them. You want to include them in your development. Yes. And so with that, I'm happy to talk about your deeper questions that are starting to fill up the chat. This is great. In summary, how do we get to a smart bionic eye? I think computer vision has the potential to improve current devices by highlighting important obstacles and so on and so forth. But to provide meaningful solutions, we need a better understanding of the neuroscience, right? This neural code of vision. How can we produce shapes that don't just fade away quickly or are super distorted? How can we provide useful artificial vision? And the phosphine simulations, I think, play a big part, because they're based on real data, psychophysically validated, and they provide theoretical predictions that might otherwise not be possible or misleading if you just look at the scoreboard model. right? So this together can help us design the new implants and test them out by incorporating all this information about the distortion of phosphines. And then, of course, there's a big engineering challenge because you have to design not just tiny implants that are safe, but now you also have to put in computer vision systems that work in real time in a low power environment and don't lead you to run into an oncoming car or something. So there's still a lot of challenges that need to be solved. But overall, I think this technology has great potential. And so with that, I'd like to end here. Thank you very much for your attention, and I'm more than happy to move to your questions now.
Great, thank you very much. Let's see, so there's some questions in the chat. Do you want to read those out to start with, or do you want me to read those?
I can read them. Okay, let's see. Can the shape of the grid be changed to match the axon smearing of the patient? So not a grid, but a different pattern. Yes, great question. We've done that. Do I have a slide? I don't have a slide, but yes, that's exactly what we asked next. So if you know there are these axons in the retina and this axon map in the retina, why would you build a square grid? Makes no sense, right? You could arrange the electrodes differently such that every electrode falls on a different axon. And so we have started doing that in simulations, and we're hoping now that people will take notice and build the next implant with not just relying on these square or rectangle grids. And then the next one was, what are some goals that chart with optimized numerals HNA? Let's see, what was that about?
That was just, I think, the standard numeral set.
I was just noticing that number example, that would be good enough for somebody to read a book.
Oh, I see.
But then, I was thinking different problems that you want to help a person with, there must be a continuum of difficulty for you to help with those problems, right? Walking across the street would be more difficult. Driving a car is way out. So have you thought about a kind of continuum of helpful problems to work on or show patients and work with people on?
Yes. So far, the assumption or the approach has been that you have this one encoding, even if it's not scoreboard, it's something that is fixed. And then you try these different tasks to see how well your implant works. But I've become of the opinion that you might not find a one-size-fits-all solution, because as you just pointed out, if reading and navigation have vastly different parameters, right? And so it could be more useful to think of this bionic guy as providing a set of tools that are useful in different scenarios, and then find the strategy that works best for the specific use case. So yeah, while this HNA thingy might work well for digits, it might not work so well in other scenarios. And that's okay, because you could have these different modes, right? You're now in reading mode versus navigation mode, and the implant could switch.
Let's see. There was also a question about what exactly is RP? Doesn't affect the optic nerve, preventing the use of the retina.
Right. So RP is a hereditary disease of the retina. Like AMD, it starts with damage to the RPE, the retinal pigment epithelium, which provides nourishment to the photoreceptors. So without nourishment, the photoreceptors start to die, and that starts a cascade through the retina. So as the disease progresses, basically the entire retinal network degenerates, meaning cell loss, meaning migration of cells, new connections, non-functioning weird connections. So the retina of an RP patient looks vastly different from the nicely layered organization I showed you. But it does not affect the optic nerve. So that means you could have, even when you're completely blind, turned blind through RP, you could have an optic nerve implant or a visual cortical implant, anything that is after the damaged region, to help with that. And so that's the appeal of cortical implants, that they can treat many more diseases, not just retinal diseases, optic nerve diseases like glaucoma, and then any sorts of trauma to the visual system, as long as you place the implant after the damaged region.
Robert, you have your Zoom hand raised.
Oh yeah.
Oh, yeah. Wow. Thank you. Wonderful presentation.
Thank you.
So I'm wondering, is there any way to go to a higher level in the brain to do an implant? Or do you have to do it at the lowest level of the visual cortex?
People have tried all sorts of regions in the brain, in the visual pathway. V1 the primary visual cortex seems to be most robust at eliciting phosphines, but you can also get phosphines in V2 and V3. And so in fact, one implant that we're currently working with implants somewhere in V2 or V3. It's kind of hard to say, but it most likely has to be early visual cortex, because we know, there have been electrodes implanted in higher regions and they do not elicit a phosphine.
Oh, but I wasn't talking about eliciting a phosphine. I was just wondering, like, if you're talking about doing computer vision, then it would be doing some of the early processing. And I'm just wondering if you tapped in to a higher level that you're not getting phosphines, but you're actually like getting higher level features, right?
Yep. Okay, I see. Yes, I would think that would be possible. And potentially useful. The challenge is, of course, that the higher you go in the visual hierarchy, the more complex the response properties are. And vision is a distributed code as well. So you have to be able to cover a large part of the population and understand the response properties of that population such that you can mimic the natural processing. But yeah, we've often wondered if maybe you need 2 implants in different areas to kind of support processing across the visual hierarchy.
I was wondering, with a cortical implant, do you have the sort of streaking issue, or is it a more scoreboard-like arrangement?
It's not streaky like due to the axon map, but the shapes are still hard to predict. So it's not a scoreboard per se. Some electrodes do give blobby percepts. So if you look in the classical literature, single electrodes often give blobs. Then you turn on 2 electrodes at the same time. You do not get 2 blobs. You get a triangle. I don't know. Simple geometric shapes often, but hard to predict.
Interesting. And then as far as like, is the training of the mechanism of like the encoder decoder, is that a machine learning kind of training?
Yeah.
Okay.
Yes, I skipped over that. Yeah, that's a deep neural network basically, that has our pulse to percept phosphine model in the loop, and so it's trained on existing data, and currently we're trying to adopt it such that you can adapt it for new patients with minimal training data. That's sort of the idea, because
using some data from other patients.
Yeah, hoping that there is a small number of parameters we need to tweak. So you could start with a general model trained on all the data we have available, and you add a little bit of patient-specific model on top, and we're hoping that will give a good patient-specific model.
Okay. Other questions? Anyone, feel free to speak up. I noticed that there were some of the dots that didn't seem to elicit any response. And does that mean that they're just not on top of an axon, or that the axon has degraded due to disease, or?
Oh, in the earlier slides,
Yeah.
early slides. Okay. No, we just did not try all the electrodes.
Oh, okay.
Yeah.
Mhm.
It does happen that sometimes electrodes do not elicit a phosphine. You know, maybe 5 out of 60 won't do that. And it's, I don't know, there's so many reasons, possible reasons for that. It could be that, yeah, in later stages of RP, the ganglion cells move more inwards. And so the neurons closest to the electrode might be inhibitory neurons like amacrine cells, that when you stimulate them, they don't give you the sensation of phosphine, or the cells are just dead. It's really hard to say.
Right. Mary?
Yeah, this is just a comment. I remember maybe 15 years ago, maybe 20, we had a talk from someone in the geography department about using a walking stick with electrodes in the bottom to describe where the person was, close to a curb, not close to a curb, etc., etc. We've come a long way, baby. May not be there yet, but we're coming. Very interesting talk.
Yeah, thank you very much. There's and there's still so much to do.
Oh, I know, I understand that.
Yeah.
Any other questions?
Yeah,
Well,
this is George.
okay.
This is George Baker.
Okay,
I
George.
tuned in late, so you may have covered this, but I'm just wondering, how are these devices powered, and how long does the power last?
I skipped over that. There's typically an external component that is battery powered, and then there is a wireless coil in the case of Argus 2. So the power is relayed wirelessly then to the implant in the eye. The battery pack lasts for a day, maybe, so they typically have to recharge it every night, like our smartphones.
Thank you.
Anyone else? Well, thank you very much. Oh, Mary, you had another one.
One more question. So
Yes.
is there any way that you get interference? If you're using one of these systems, if you also want to use earphones or whatever, I mean, how do you, can you program this in a manner that you don't get interference from one device to another?
Right. I'm not aware of interference, between the implant and the headphones or anything, because it's all fairly localized. There could be interference, crosstalk between electrodes, or if you start having more than one implant, I can definitely see that being an issue. But so far, I'm not aware of the implant interfering with headphones or anything. Yeah.
Thank you.
And if you stimulate two, is it always constructive things, or are there interference? Made me think of negative interference, like canceling out.
Electrodes, so making the phosphine appear where you don't have any physical electrode placed.
Oh,
So that's I guess a good use of interference, right? But in other cases, it can be destructive, or it can inhibit. And people typically try to use a multiplexing scheme to kind of deliver current to one electrode after the other in quick succession to avoid electrical crosstalk and stuff.
okay. Great. Robert?
Yeah, somewhere I missed something basic, which is when the retina is working properly, there's a grid of photoreceptors and there's no streaks or anything like that. why is it that you can't stimulate things the same way?
It is a problem with the epiretinal implants just because they are placed on the axons, and the axons have a lower activation threshold than the somas. So whenever you stimulate, you get axons. It's not a problem in natural vision because we have the photoreceptors that are the only ones responding to light, right? And so in natural vision, light turns on photoreceptors and the signal propagates like that. But with electrical, you're just blasting tissue, right? You're just hitting everything in your vicinity, which includes axons.
Oh, so you're not stimulating the rods and cones, you're just stimulating the nerves that the rods and cones connect to? Is that a naive way of understanding this?
In the implant, yeah.
Yeah.
So the rods and cones are gone, right? In RP.
Okay.
And, yeah.
Uh-huh.
So you have to go to the next ones. Mhm.
Okay. I see. Mhm.
Yeah.
Great. Thank you very much.
Mhm.
I appreciate
you.
it. And we'll let people know the YouTube link when that comes out. So great.
Sounds great.
Thank you
Thank
very
you
much.
very much.
Okay.